Another property of water that is important for biochemistry is the ability to ionize. So water, of course, itself is a neutral molecule, but the water molecule has the ability to split into a proton and a hydroxide ion. So that is, again, a property of lots of molecules, and in fact, molecules that give up protons we call acids, and molecules that either take up protons or produce hydroxide ions we call bases. And so water, in a way, is both an acid and a base at the same time. But it only carries out this reaction at a very small rate. So if you have a molecule of water, it will consist of a molecule of water we know is an atom of oxygen and 2 atoms of hydrogen. So when it ionizes, it becomes a free proton with a positive charge and a hydroxide ion with a negative charge. Now in reality, the proton itself doesn't actually exist for very long. It eventually reacts with another water molecule to form what's called a hydronium ion. So it's an H3O plus, but the effect is basically the same. And of course, this reversible reaction happens too. So if you have a proton and a hydroxide ion, or hydronium ion and a hydroxide ion, you'll go back to just a molecule of water. And this reaction, like any chemical reaction, has a equilibrium associated with it. So we know that water is just 2 atoms of hydrogen and 1 of oxygen. And when it ionizes, it becomes a free proton plus a hydroxide ion. Now in reality, of course, the proton doesn't exist by itself for very long. Instead, what happens is it combines with another water molecule to form hydronium, so H3O plus, but it's easy enough to just depict it this way. And this is reversible, so a proton and a hydroxide ion together will go back to being a water molecule. And so a solution of pure water or water in solution will at any given time be in some sort of equilibrium where these both forward and backward reactions are occurring. And so the equilibrium constant for this reaction is this. So the equilibrium constant is the ratio between the proton concentration times the hydroxide ion concentration divided by the water concentration. Now, the concentration of water, you can calculate just by saying, if you know the density of water and the molecular weight, you can show pretty easily that for pure water, and indeed for pretty much any aqueous solution where water is at a much higher concentration than any other molecule, concentration of water is about 55.5 moles per liter. So that means that the equilibrium constant is just the product of proton concentration and the hydroxide ion concentration divided by 55.5 molar. So it's a lot easier to just combine 55.5 molar is basically a constant no matter what the concentration of protons or hydroxide ions is. The concentration of water will still be pretty high, pretty close to 55.5. So we can combine those two constants and just say that the product of the proton concentration and hydroxide ion concentration in water is equal to the equilibrium constant times 55.5 molar. And those two together we call Kw. So that's a special equilibrium constant just for the ionization of water. And it turns out that the equilibrium constant for this reaction is about 1.8 times 10 to the negative 16th. So Kw is that times 55.5, and it works out to about 1.0 times 10 to the negative 14th. So what that means is that in pure water, the concentration of protons times the concentration of hydroxide ions is equal to, actually it doesn't matter if it's pure water or not in any solution, it's these two values multiplied together. In pure water, all of the protons and all of the hydroxide ions came from water, therefore they should be equal. So again, for pure water, we can just go ahead and say that this value is equal to this value. Therefore, both of them are equal to the square root of this number here. So in pure water, the proton concentration should be equal to 1 times 10 to the negative 7th. And rather than, whenever you're dealing with very small numbers like this, it's easier to just describe them in terms of their that power of 10 there. So we use this notation called P. So P for H is just the negative log of proton concentration. And so that's, again, in this case, negative log of 10 to the negative 7th. And that's just equal to 7. So when we say that the pH of water is equal to 7, what of course we mean is that the hydrogen ion concentration is 10 to the negative 7th. And that's why the pH of water is equal to 7, because the hydrogen ion concentration is 10 to the negative 7th, and the reason for that is because the equilibrium dissociation constant of water, Kw, is 1 times 10 to the negative 14th. Now, that's also why we consider water, or a pH of 7, to be neutral. So any solution with a pH higher than 7, which means that the hydrogen ion concentration is larger than 7. So anything with a pH larger than 7, that means that the hydrogen ion concentration is less than 10 to the negative 7th. We call basic anything with a pH lower than 7. That means the hydrogen ion concentration is greater than 10 to the negative 7th. We call it acidic. And so the pH scale, again, is convenient because a significant change in proton concentration has to be at least a factor of 10. So if we say, again, water is at a pH of 7, if we measure the pH of a solution and it's a pH of 6, that means that the hydrogen ion concentration is 10 times greater than it would be in water. Again, water has a pH of around 7, or plain water has a pH of 7. Most biological systems, biological aqueous systems, are also pretty close to neutral. So most human bodily fluids are pretty close to 7, with the exception of things like saliva, which is a little more acidic, and then gastric juice. That means the juice, digestive fluid in your stomach, actually has a very low pH and is very acidic, even more so than, say, lemon juice, which we think of as being pretty acidic, all the way down to a solution of hydrochloric acid. So a 1 molar solution of hydrochloric acid would have a pH of 0 because its hydrochloric acid is a strong acid. It completely dissociates in water, and so its pH is always going to be 0 because that would be a hydrogen ion concentration of 1 molar. At the other end, you have basic solutions. So seawater is a little bit more basic than plain water, and at the very high end, you have things like ammonia and bleach, which are used as cleaning solutions because they take protons away from solutions, and so at very high pHs, you have very low proton concentration all the way up to a 1 molar solution of sodium hydroxide. Again, that salt will completely dissociate in water, and so 1 molar sodium hydroxide would mean 10 to the minus 14th molar concentration of protons. So again, that's just basic review of kind of how acids and bases work, and what it means to be acidic or basic. But weak acids and bases are those solutions that kind of fall somewhere in the middle between something like hydrochloric acid and sodium hydroxide. So if you put a weak acid or into an aqueous solution, some of it will dissociate into a proton in its conjugate acid, but some of it will, or conjugate base, but some of it will stay in its acid form. So for example, acetic acid, this is acetic acid here, in water, dissociates into acetate, this is acetate, and a proton. Typically, some of the acetic acid will remain as acetic acid, and only some of it will dissociate. And so when we have a weak acid like this, and it dissociates in water, in this case, the negatively charged ion that forms we call the conjugate base, and the original acid we call the conjugate acid. So a weak base, like ammonium, so it's a NH4 plus molecule, it dissociates into NH3 and H plus. Actually, NH3, sorry, ammonia, this is the weak base. And we consider it a weak base because it mostly will remove protons if you add it to solution, but this again will stay partially in its ammonia form and partially in its ammonium form. So these are all examples of weak acids and bases. And what's important is that each one has its own dissociation constant. In fact, you can measure the strength of an acid by that dissociation constant. So again, acetic acid has a pKa. So again, pK, that means the minus log of its equilibrium constant. So that's the product of, again, the acetate concentration times the proton concentration divided by the acetic acid concentration at equilibrium. And the minus log of that is about 4.76. So that means the Ka is close to 10 to the negative 4.76. And so anything with a lower pKa is actually a stronger acid than anything with a larger pKa. So again, ammonium has a very large pKa, so 9.25. So that means it's a very weak acid. In fact, ammonia is actually a relatively strong base. And so these are all called monoprotic acids because they only really have one proton that they can give up. But you can have diprotic acid. So for example, carbonic acid has these two protons that it can give up, so it can dissociate into HCO3 minus, and then HCO3 minus can dissociate into which is called bicarbonate, can then dissociate into just the carbonate ion, CO3 2 minus, and each of those has its own pKa. So the first one has a relatively low pKa, and the second one is relatively high. So the first one to come off makes it a stronger acid. And you can even have things with 3 or more protons. So phosphoric acid is a triprotic acid. So H3PO4, that's phosphoric acid, and it can then dissociate into dihydrogen phosphate and a proton, and dihydrogen phosphate can become monohydrogen phosphate, and then monohydrogen phosphate can become just inorganic phosphate. And each one of those reactions, again, has its own pKa. But again, the idea of pKa only really has meaning in the context of weak acids. So if you have a very strong acid like hydrochloric acid, so the reaction for hydrochloric acid would be, HCl dissociates into H plus and chloride. But the reality is this reverse reaction is not going to happen very much. So the dissociation constant for this reaction becomes basically the HCl concentration would be so low that the Ka for this would be essentially infinite. So it would be so big that you couldn't really measure it. And so the pKa would effectively be very close to zero, or essentially not undefined. But that's okay, because again, we're concerned with weak acids and bases because they're the ones that are more important for biological systems. Hopefully your cells are not being exposed to hydrochloric acid or sodium hydroxide very much, and so you don't really need to worry about their effects on normal behavior of your cells. Now, if you want to know the pKa, which again, that's a constant for every one of these weak acids, if you want to calculate it, you would do so by titration. So what that means is you start with a solution of your acid, and then you add either add hydroxide ion if you're starting from the acid form. And so as you add hydroxide ion, what should happen is the pH should go up. And with these weak acids, what happens is when they get close to their pKa value, the rate at which the pH changes when you add hydroxide will slow down. And the reason is that as you get to the point where the concentration of conjugate base and conjugate acid are equal, what that means is you're getting close to the point where the pH equals the pKa. And so the adding more hydroxide ion will have less of an effect on increasing the pH until you start to get away from the pKa, and then it starts to go up again. So you can, once you get to this inflection point where the slope of that line starts to change, that is where you have reached a pH that's equal to the pKa, and so you can determine it empirically that way. And again, different acids have different pKa values. So for acetic acid, it has a pKa of 4.76. So if you were to titrate it, you would see that pK show up at a pH of about 4.76. This is the titration curve for dihydrogen phosphate. Again, that's the diprotic form of phosphoric acid. And this is the titration curve for ammonia. So again, this is just how you determine the pKa value of a weak acid. So another important feature of weak acids is that they act as buffers. What that means is if you have a solution that contains a weak acid plus its conjugate base at about equal concentrations, it will resist a large change in pH. And the reason for that is due to the fact that, again, a weak acid and a weak base have their own dissociation or equilibrium constant that they must obey, and then water has its equilibrium constant that it has to keep to. So let's say you have a equimolar solution of acetic acid and acetate. That means if you add, let's say, proton, so you try to lower the pH by adding an acid, a strong acid, then those protons, when you first add it, will react with the acetate and drive this equilibrium to the left. So it'll convert the acetate ion, the conjugate base, back into acetic acid. So instead of actually increasing the proton concentration, all you're doing is increasing slightly the concentration of acetic acid. And then if you drive it the other way, if you try to add hydroxide ion, try to raise the pH, then those hydroxide ions will react with the acetic acid to give you acetate. And so that's why all these weak acids again, have this kind of flat part in their titration curve, because that's where the pH is getting close to the pKa, and at that pKa, the concentration of conjugate base and conjugate acid are, by definition, are exactly equal. And that's why they are good buffers. And so each one also has a buffering region, because once you get to a certain point, once you get to about plus or minus 1 away from that pKa, then they cease to be good buffers. So again, here for acetic acid, you can see that within this region, so from pH 3.76 to 5.76, the slope of this curve is relatively flat. So that means that, again, a relatively large amount of hydroxide ion that you're adding has a relatively small change in pH. Whereas when you get outside that range, so you get above pH, let's say 5 or 6 into this area, adding hydroxide ion has a much greater increase in increasing the pH. Same thing at the lower end. So when pH starts very low and you have you're below pH 3.76, adding hydroxide ion has a much bigger effect. So that's why we call it a buffer, because it maintains a pH in that range. And if you're making a solution and you want to keep the pH within a certain range, you would choose an appropriate buffer. So if you want to make a solution that has a relatively constant pH that's relatively high, you might make an ammonia with a buffer. A buffer with ammonia. At the other end, again, acetic acid has a relatively low pKa, so it would be good for making solutions that you want to maintain at a low pH. And so, again, every weak acid has one of these constants, and if you want to make a buffer that has a certain pH, you just find one that has a pKa close to the pH you want to buffer at. And at any given time, you can use the equilibrium constant. If you know either the pH or the acid concentration, you can calculate the other. And to do that, you use the Henderson-Hasselbalch equation. But really, the Henderson-Hasselbalch equation is just a modification of the equilibrium constant, because again, Ka equals proton concentration times the conjugate base concentration over conjugate acid concentration. So if you just take the negative log of both sides of those, then you've got negative log of Ka is just pKa, and then negative log of proton concentration is just pH, and then you have the negative log of the conjugate base over conjugate acid, and then just rearrange that in terms of pH. So at any given time, you can calculate pH given the concentration of your acid or base, and vice versa. So again, this is just showing different buffers in their buffering regions. Now, the reason this matters, again, why we care about pH, is most biological reactions, chemical reactions, only really operate within a narrow pH range, especially enzymes. So we'll talk a lot about enzymes later. Enzymes, we already said, though, are proteins that help reduce the activation energy of reactions and therefore make them go faster. But most of them, their activity depends on pH. So typical enzymes prefer kind of neutral pH, but there are some that prefer more acidic pHs. So pepsin, for example, is an enzyme that breaks down other proteins, and it actually has an optimal activity way down at pH 2. So it's just that at that pH, its conformation, its shape, is ideal for the reaction it catalyzes, and that's because that enzyme is part of your digestive juices. So there are cells in your stomach that secrete pepsin into your stomach, into your digestive system, and they're there to help break down proteins in your gut as you digest your food. Protein like trypsin, on the other hand, is a more typical intracellular enzyme, and so it prefers pH that's close to neutral. Whereas alkaline phosphatase, the reason it's called alkaline is that it prefers a pH all the way up here at like 8.5, 9. So it prefers more basic solutions. Now that doesn't mean they don't work at different pHs, just that this is the optimal activity where you see the peaks. So that's why the pH matters, and that's why the pH needs to be maintained. So in cells and in bodily fluids, you actually have natural buffers, things like phosphate Bicarbonate are weak acids that are found in cells, and they in part help maintain the pH within a narrow range. And the pH of your blood and your bodily fluids is also maintained by various systems in your body. So, for example, the bicarbonate system is actually maintained by the amount of carbon dioxide. So, in fact, if your blood pH gets too low, if it becomes too acidic, one of the things that happens is there's actually a sensor in your brain that detects that, and will actually increase your breathing rate in an attempt to actually increase or get rid of CO2 from your body, and that will then lower or raise the pH, because it will get rid of protons as they are leaving through the bicarbonate buffer system. All right, the last thing to say kind of about water before we move on is that water is, up until now we've been talking about water really as if it was just sort of a passive bystander, just sort of the medium in which all these other biochemical reactions are occurring. But water can also act as a reactant in various biological reactions or biochemical reactions. And there are basically two major types of reactions that involve water. So condensation reactions are ones in which two reactants combine, and in the process they lose an atom of hydrogen and a hydroxide ion to form water. And so we call this condensation. This is a condensation reaction because a molecule of water is formed. So here in this case we're converting ADP into ATP, or just anything with a phosphate, one phosphate into two phosphates. So one phosphate loses a hydrogen, the other one loses an OH, and you form a new bond called a phosphodiester bond, or sometimes called a phosphoanhydride. The reason it's called anhydride is because it formed by losing that water molecule. So there are reactions that produce water like this. In fact, water is produced through a lot of metabolic reactions, and some animals actually are able to survive in relatively arid environments by producing water through the breakdown or through the formation of other molecules. And then the opposite of a condensation reaction is hydrolysis. So hydrolysis occurs when a molecule is broken up into two or more other molecules, with a water molecule being one of the reactants. So, for example, acetylcholine breaking down into choline and acetic acid, that's a hydrolysis reaction, because this OH group here gets attached where this bond is right here, and then a proton comes off as well, but now you have a molecule of choline and an acetate. So that's just an example of a hydrolysis reaction. All right, so that pretty much is all I'm going to cover from this chapter. So next time we will get to chapter 3.